Hello and welcome to day 24 of Advent of Code 2024. So this is the second, almost the last day of Advent of Code 2024. Yeah. So this problem is called crossed wires, and I had actually a lot of problems with the part 2 of this problem, and so this video will be kind of a little bit different than the previous videos I've done, because for part 2 of this problem I actually needed a lot of help solving it, and although I do have a generalized solution to solve this, but but I'm not that good at explaining these stuff. So but I'm going to show you, and I'm going to try to explain what's going on. So you and the historians arrive at the edge of a large grove, somewhere in the jungle. After the last incident, the elves installed a small device that monitors the fruit. And while the historians search the grove, one of them asks if you can take a look at the monitoring device. Apparently it's been malfunctioning recently. So the device seems to be trying to produce a number through some Boolean logic gates. So each gate has 2 inputs and 1 output. So the gates all operate on values that are either true or false. And gates output 1 if both. And gates output 1 if both inputs are 1. So if either input is 0, these gates output 0. So this is basically an AND, a bitwise AND. Or gates output 1 if one or both inputs is 1. If both inputs are 0, these gates output 0. So it's a basic bitwise OR. And this is an XOR. So XOR gates output 1, and if the inputs are different. And if the inputs are different, if the inputs are the same, these gates output 0. So this is basic XOR. Gates wait until both inputs are received before producing output. Wires can carry 0, 1, or no value at all. There are no loops. Once a gate has determined its output, the output will not change until the whole system is reset. Yeah, so each wire is connected to at most one gate output, but can be connected to many gate inputs. Rather than risk getting shocked while tinkering with the live system, you write down all of the gate connections and initial wire values, which is your puzzle input, so you can consider them in relative safety. So here we see an example. So we see kind of the initial state of some of these wires. Then we see kind of a list of formulas. So it will be kind of, so this means that x00 will be x00 and y00 will be directed to the z00, and this will be x01, which will be XORed with y01 and directed to z01. So that's what these formulas mean. So because gates waits for input, some wires need to start with a value, and that's these starting values here. Yeah. The first section specifies these values. For example, x01 means that the wire named x00, x01, x00 starts with the value 1. The second section, as I just described, lists all these gates and the wires connected to them. For example, x00 and y00 is directed to z00. Describes an instance of an AND gate which has wires x00 and y00 connected to its input, and which will write its output to wire z00. So in this example, simulating these gates eventually causes 0 to appear on wire z00, 0 to appear on wire z01, and 1 to appear on wire z02. Ultimately, the system is trying to produce a number by combining the bits, and on all the wires starting with Z, Z00 is the least significant bit, then 0, Z01, and then Z02, and so on. In this example, the three output bits form the binary numbers 100, which is equal to the decimal number 4. So here we see a larger example. And after the calculation has been done, we will have this result. And as we are only interested in the Z wires, so we will just look at them. We will kind of combining the bits from the wire starting with Z, which produces this binary number, which and when we do this, we need to also sort them in kind of we need to reverse the order, because this will be the least significant bit and this will be the most significant bit, so to speak. Yeah. So if we do this for this example, we should get decimal number 2024 in the end. So this is a pretty straightforward problem actually, and I will try to do this a little bit quickly. So we will have kind of we will define a couple of dictionaries here. But to begin with, so we will have a kind of a dictionary of our known values, which will be kind of, yeah, I'll also need to grab this input here. So these will be kind of our, this is what our known values will be. And also we will have our formulas, which will be the next section, like these here. And we will also define these operators. So this will be kind of a, this is actually a new way I explored a little bit, because to define these operators as functions in a dictionary. So we can define the NOR, which will be the bitwise OR between X and Y. We define an AND, which will be the bitwise AND, and this will be kind of the XOR. So this way we can call them a little bit more intuitively. Then we will kind of arrive at what is usually our kind of starting point for every puzzle in AOC. We also read our input. So we will kind of do our read in our input as we read the entire text, and I will use my previously defined function, which is like splitting by the new line. As we remember here, we have a kind of a double new line here. So we will have those in blocks. Then we will kind of first take our known values, parse them. Then we will kind of take our formula block and parse that. And you can see we will kind of replace this sign with a so the formula will kind of be in the form of that the key will be the wire the formula is directed to. That's why because we split them by the blank line, and then we or by space, and then we kind of take the last part, and like, so we take, if this was the case, we will take this will be kind of the key in our formulas dictionary, and these three parts would be kind of the value. So that would be kind of the tuple value that we would have in our formulas. Yeah. So after we have kind of parsed them, then we will do our calculation. Yeah, we will also add kind of our evaluation function, because when we do these calculations, we need to do it in a kind of recursive way. But we will just add the other code first. So we have kind of we have our list of our SED wires. We will kind of keep that list, and then we will kind of loop through these until there is nothing left, or we will actually, I mean, we will break when we don't find any more SED keys, SED wires actually. So this we will kind of first construct our key, which will be SED, and we will also always pad left. So we will always kind of pad them with 0. So we will start with will be kind of, if I is 0, we will kind of say SED 0 0. Then we will set SED 0 1 0 2 and so forth. So that's how they are constructed. And as I said, when we don't find any more, we will break, and then we will kind of call our eval function with that key. So the eval function will kind of first we will check if our known values contains that wire, then we'll just return that known value. Otherwise, we will kind of parse out our formulas. It will be our operator, our x and y, and then we will kind of create a known values dictionary item using these operators and sending in the eval of x and the eval of y. So that will kind of make a recursive jump here. And if we kind of find it, we will return it. Otherwise, we will kind of do so that will be kind of a recursive operation, finding all these values, and in the end, we will kind of return that dictionary item back, or actually we will return what the value is for that known values for this wire. So that will be where we kind of collect our bit values, and then we kind of do this loop. Then to form our binary string, we will as you said, we will go from the 0 up to the last one, and then what we need to do is to kind of construct our string. We'll take this as a numerable. We do a reverse, then we will select it. So we kind of do this in that sense. And so after this, we will kind of get our binary string reversed, and then and the last thing to do is actually convert our binary string to a decimal, and that can be easily done with the convert to int64 with the base 2. So if we run this, we should have 2024. Yeah, so we have 2024. So this is kind of the straightforward solution for part 1. This is what I actually did when I solved it, or mainly what I did when I solved it. But then we kind of come to part 2. So we can first look at this. So part 2, and let's kind of read what this text says. So after inspecting the monitoring device more closely, you determine that the system you're simulating is trying to add two binary numbers. Specifically, it's treating the bits on the wire starting with X as one binary number, treating the bits on the wire starting with Y as a second binary number, and then attempting to add those two numbers together. The output of this operation is produced as a binary number on the wire starting with Z. In all these three cases, wire 0, 0 is the least significant bit, then 0, 1, and so on. Yeah. The initial values for the wires in your puzzle input represent just one instance of a pair of numbers that sum the wrong value. Ultimately, any two binary numbers provided as input should be handled correctly. That is, for any combination of bits on wire starting with X and wire starting with Y, the sum of the two numbers those bits represent should be produced as a binary number on the wire starting with Z. For example, if you have an addition system with 4 X wires, 4 Y wires, and 5 Z wires, you should be able to supply any 4-bit number on the X wires, any 4-bit number on the Y numbers, and eventually find the sum of those two numbers as a 5-bit number on the Z wires. One of the many ways you can provide numbers to such a system would be to pass 11 on the X wires and 10, 11 in binary, and then 13 on the Y wires with 11, 0, 1 in binary. Yeah. If the system were working correctly, then after all gates have finished processing, you should find 24 on the Z wires and the 5-bit as the 5-bit binary number 11000. Unfortunately, your actual system needs to add numbers with many more bits and therefore has many more wires. Based on a forensic analysis of scuff marks and scratches on the device, you can tell that there are exactly 4 pairs of gates whose output wires have been swapped. A gate can only be in at most one such pair. No gate's output was swapped multiple times. For example, the system below is supposed to find the bitwise AND of the 6-bit number on the X00 through X05 and a 6-bit number on Y00 through Y05, and then write the result as a 6-bit number on Z00 through Z05. Yeah. However, in this example, 2 pairs of gates had their output wires swapped, causing the system to produce wrong answers. The first pair of gates with swapped outputs is X00 and Y00 to XZ05 and X05 and Y05 to Z00. The second pair of gates is X01 and Y01 and Z02 and X01, 02 and Y02 to Z001. Correcting these two swaps results in a system that works as intended for any set of initial values on wires starting with X or Y. So in this example, 2 pairs of gates have outputs that are involved in a swap. By sorting their output wire names and joining them with commas, the list of wires involved is, this list. Of course, your actual system is much more complex than this, and the gates that need their output swapped could be anywhere, not just attached to a wire starting with Z. So basically what this puzzle part need us to do is to find which four wires we need to swap, or which swaps we need to do, and what these wires that we have swapped, to fix our system we need to add those swaps. So I was kind of stumped when I saw this, and I didn't actually know how to solve it, and it turns out you basically need to inspect your input. You can find some of them. What I did was that I actually looked for help on the Reddit site, because I want to learn how to do this, and but this is kind of a little bit beyond my comprehension. But I do have, in the end, written a kind of generalized function. or a generalized solution that could be applied to any input. So, but it's a little bit slow at the moment. So what I'm going to do is I'm going to try to show you kind of a little bit what's going on. So this is I'm just going to bring my real code over here. Yeah. So this is kind of my real code here for this problem, and basically we're going to actually look at what so basically what I did was to write a number of verify functions. So these were actually used both when I kind of debugged my own input file, and also they're also used for this generalized solution, of course. So what we need to do is kind of verify we need to verify our Z values. So we need to verify our intermediate XOR, verify our carry bit, verify our direct carry, verify our recarry. So these are all these methods, and what they do is check. They kind of go. Some of them are recursive, some are not. And we can look at this as a tree. So when we check a wire, we need to check that the wire values are correct, and these kind of verify functions will verify that they are correct. But the thing is that I'm not very good at explaining what this is, because I've gotten a little bit help to fix these, and so I can't really say exactly what these functions what the thinking was behind it, basically. But basically what we're kind of doing is the solution for this is that we need to kind of keep a list of swaps that we need to do. So we kind of call our progress function. That function will kind of do in turn call the verify, which will then call the verify Z. We will kind of start with the 0. We will verify that the 0 is, if that is correct, we will kind of move on to the next, and as long as verify returns true, we will kind of just loop, and when verify suddenly returns false, we will come back from that. So we first we kind of take our input and just go to our list and find the first wire that is failing, basically, and that in my case it was Z05, I think it was. And then what we need to do is to try to actually swap these. We will try a set of swaps, and swap and actually do the progress again. So we will kind of swap our formulas and then call our progress. See if this swap worked, then we will kind of increase our progress. So then so that we, for instance, if we were at Z05, we will and we do a swap. Then if the next stop is higher than 5, then that swap worked. So then we can kind of break and try the next and do the next kind of thing. And this kind of method will work, and in the end we will have all what the swaps are, and well, I can actually run it now. So this will be my what calculates the first is my part 1 answer, then it will take a little bit of time, and then in the end we will have our part 2. It will kind of take some time, yeah. So you see, it's not a very performant solution, but this is my answer for part 2, and we can verify that that is the same. So that's kind of my generalized solution for it. And well, as I said in the beginning, it's a little bit strange video because I'm not that good at explaining these things, because this kind of has a lot to do with how to calculate bit values back and forth. So I kind of looked for pointers on the Reddit site. I looked for kind of other people who have solved it. So that's how I came up with my solution, basically. So yeah, that's the thing. Is that this was basically out of my. This was not a thing I would probably have solved if I didn't kind of looked around a bit. So yeah, so this is I can say right now that these are not problems that I'm very comfortable with, because mainly problems that needs you to actually debug the input file, basically. That is I mean, some people like it. I don't really like it. I like problems with a kind of a clear scope, what to do, and this is actually not that, I think. Yeah, so so this will be my video. I mean, this video will come out a day late. It's already 25th right now, so I've already solved day 25, so I will kind of do that video right after this. And yeah, so see you on day 25 then.